In today's world, where power systems drive technology to a whole new dimension, one thing that remains not negotiable is electrical safety. Every second across manufacturing plants, data centers, refineries, and critical infrastructure, lives and assets depend on precise decision made in face of complex electrical challenges. But how do you confidently move from raw data to clear and actionable insights that protect people and productivity? That's where ETAP Analyzer tool redefines the standard. Hi everyone, I'm Raghu Veeraraghavan from ETAP, and I'm excited to show this intelligent platform meticulously designed to think from the engineer's point of view on breaking down complex results into simpler safety solutions using the ETAP short circuit and arc flash analyzer. In this presentation, we will identify some of the most critical challenges in short circuit and arc flash analysis. And then we will demonstrate some of the user-friendly solutions provided in ETAP to address these challenges with key takeaways. Behind every reliable power system lies an ocean of complexity. Electrical engineers are tasked with ensuring safety and compliance with managing thousands of variables that can make or break a study. From the start, data collection itself is a challenge. Generator decrement curves, utility fault contributions, cable schedules, relay settings, and system configurations must all be precise and up to date. A single missing parameter can lead to misleading results. In device duty and arc flash protection, the array of rules and standards add another layer of difficulty. Engineers must evaluate not just three-phase faults, but also single-phase line-to-ground faults and even special locations such as remote or underground installations. Each configuration, open or closed transitions in ATS, which is the automatic transfer switch, sensor placement, or enclosure size can drastically alter the outcome. Troubleshooting is further complicated in complex networks. Multiple sources in parallel, standby generators, or evolving utility data which contributes to shifting fault levels. Add in maintenance switching, breaker coordination, or arc flash mitigation strategies, and suddenly the task is more than just an analysis. It's a balancing act of safety, performance, and compliance. And with modern facilities producing massive data sets, the challenge isn't just the analysis. It is the processing of large volume of data, identifying what matters, where the risk is highest, and how to act on it in time. These are real-world challenges that make short circuit and arc flash analysis one of the most demanding yet critical responsibilities in power system safety. Let's take a closer look at one special case in short circuit. Consider evaluating a device duty case on the secondary side of the transformer. Now, here's a question. Which fault would you expect to be larger? A three-phase fault or a line-to-ground fault? Most engineers instinctively choose the three-phase. Why? Because it's the most severe fault. However, the proper data collection from a transformer nameplate identifies this is a delta Y solid secondary. In this case, the line-to-ground fault is greater. Why? Because the sequence network closes through the neutral, sending the current straight back to the source. Now imagine identifying these hotspots across an entire industrial facility. Data collection becomes critical. Transformer connections, grounding methods, utility contributions, and system configurations must all be accurate. A single oversight can mask a severe hazard. When protective devices are sized without considering this condition, they may appear sufficient for a three-phase duty, yet fall short when exposed to a higher line-to-ground current. Industry practice often requires settling protective device at least 15% above the three-phase rating to ensure both safety and reliability. This example highlights just how important it is to uncover these hidden scenarios. because in real-world power systems, it's not the obvious faults that catch us off guard, it's the subtle interactions, the ones only revealed when the data is modeled, analyzed, and verified with precision. And this is exactly where ETAP Analyzer tool changes the game. Instead of manually piecing together transformer data, cable schedules, relay settings, or utility contributions, ETAP automatically maps, calculates, and highlights these special fault conditions, including cases like line-to-ground faults on a delta-wide transformer that exceeds the three-phase fault. With just a few clicks, engineers can run side-by-side comparisons, visualize sequence networks, and instantly validate whether the protective devices are truly sized for both compliance and the safety margins, like that critical 15% above the three-phase duty as per the IEEE 399 standard. The result? No hidden risks, no second guessing. Just clear, interactive insights that empower you to design, troubleshoot, and operate your system with confidence and reliability. Because the complexity of the power systems will always grow, the right tool makes it effortless to see deeper, act faster, and protect smarter every time. Short-circuit studies can quickly become overwhelming, but the ETAP short-circuit analyzer makes complex analysis both simple and powerful. It performs and manages complex calculations automatically, saving time while ensuring accuracy across large facilities. Engineers can evaluate worst-case device duties, including special transformer and fault conditions that often get overlooked. It fully complies with ANSI C37 requirements for breaker duty and interrupting ratings, as well as the international standards like IEC 60909 for fault current calculations and IEC 62271 for high-voltage switchgears. This means every result is not only precise, but also globally recognized and audit-ready. The analyzer directly models generator circuit breakers, utility contributions, decrement curves, ensuring proper duty evaluation for both conventional and renewable generation sources. Results are interactive, tied directly to the one-line diagram so engineers can immediately see overstressed equipment, misapplied protections, or weak points in the network. Whether analyzing three-phase, single-phase panels or special fault cases like line-to-ground, line-to-line, and double line-to-ground, ETAP delivers consolidated worst-case reports for complete clarity. With ETAP Short-Circuit Analyzer, engineers gain more than the compliance, they gain the confidence to size, select, coordinate protective devices for safe, reliable, and standard-driven operation. And this is just the tip of the iceberg, because when it comes to arc flash, the conditions multiply, the risks intensify, and the margin for error disappears. Here's another example. Incident energy is a function of time. Identifying the magnitude of sustainable fault currents that trip protective device time current curves, especially for fault locations near rotating equipment, is a classic example of nonlinearity. Arc flash faults can happen in different locations for a given faulted equipment, involving several unknowns such as protective device isolation, the line side, load side, bus side, or motor terminals. That's where protection and coordination becomes critical. Protective devices must operate fast enough to clear arc currents, but selective enough to avoid nuisance trips. Analyzing these conditions to evaluate worst-case incident energy is a challenge. One of these challenges in arc flash analysis comes from generator fault decay and decrement behavior. Unlike utility sources, generator current does not remain constant. It decays rapidly over time, following decrement curves defined by machine design, excitation response, and system dynamics. Here's the danger. Arc duration is directly tied to arc available current. If engineers only consider the initial symmetrical fault current and ignore the decay profile, they risk misjudging how long an arc can sustain. Even with reduced current, a longer arc duration can still release enough incident energy to cause severe burns or fatalities. This is especially critical in minimum arc flash scenarios where delayed clearing and extended exposure make the hazard far greater than it appears on paper. The ETAP Arc Flash Analyzer directly resolves this challenge. Instead of showing only a single calculated value, it displays results at every stage of the generated decay curve, so engineers can trace how incident energy accumulates over time. Each stage is analyzed, integrated, and then consolidated into the worst-case incident energy, ensuring nothing is overlooked. Arc flash mitigation goes beyond calculations. Engineers must evaluate maintenance mode settings, relay coordination, zone selective interlocking, and even arc flash sensors to minimize exposure. And the system must clearly communicate with labels, warnings, and procedures so personnel know exactly what they are stepping into. This is why arc flash analysis is not just about numbers. It's about uncovering risk at every location and aligning protection strategies and ensuring that safety measures are practical, visible, and effective. And this is where the ETAP Analyzer tool makes the difference. With a single platform, you can simulate, compare, and optimize arc flash mitigation strategies, turning raw data into clear insights and actionable safety decisions. ETAP helps you see the danger before it happens and design the solution before it's too late. This stage visibility lets engineers clearly see how decaying generator contributions interact with relay pickups, breaker clearing times, and arc sustainability. From there, the analyzer makes it easy to evaluate the maximum and minimum scenarios, testing mitigation settings like maintenance mode or arc sensors, and validate whether the system truly provides safe protection. The result: an accurate, transparent, and standards-compliant analysis that reflects real-world behavior, giving engineers confidence that their arc flash study genuinely protects lives. All right, let's switch gears to show the ETAP presentation on how to learn and transform device duty analysis to arc flash analysis using the arc flash and the short circuit analyzer tool. In this demonstration, I have created several scenarios considering device duty analysis and short circuit based calculations. Like, for example, I have considered different scenarios, each of them covering several aspects, for example, such as pre-fault voltage, considering the load terminal short circuit, considering different max through fault current, or provide 10 device duty scenarios based on system configurations that we discussed about, such as main time main and multiple parallel configurations, and also different utility data and what if scenarios basically. So there's one situation for cogen, emergency, and normal, and all these scenarios that is added up here will be demonstrated significantly from the analysis point of view. And the collection of all these device duty scenarios are basically programmed into this scenario wizard, and the scenario wizard will run all the short circuit scenarios in a single shot. And the combination of the scenarios from the scenario wizard can still be programmed into the macro wizard to run the analysis accordingly. Now, after running all these analyses, the program will provide the device duty results for all the faulted locations and the associated protective devices. And to interact with the one-line diagram results and the analyzer, upon clicking the short circuit device duty or arc flash analyzer, the program will automatically provide the general tab where it tells all the summary of the system configurations and the different study case settings that is being selected for both three-phase and single-phase duty. Now, when it comes to the device duty part, the program automatically sorts down all the faulted locations and the associated protective devices such as high voltage circuit breaker, low voltage circuit breaker, generator circuit breaker, fuse, and switches according to the ones that are present in the one-line diagram. Now, once all the analysis and different scenarios are considered and after performing the device duty data, this is provided a proper data collection of the utility short circuit, the transformer nameplate data, and the motor nameplate data. The generator decrement and nameplate data is being collected successfully. Not to mention, it also includes the cable schedule and the relay settings that needs to be calculated based on the minimum and the minimum short circuit accordingly. Now, once all these data is plugged into the program will automatically execute all the scenarios based on the compliance standards that I mentioned, such as ANSI and IEEE standards, and the program will provide the device duty results. Now, all the data has been collected and it's been given to this analyzer. The program will automatically start sorting out the high voltage and the low voltage, the generator circuit breaker, the fuse, and the switch results along with the connected bus, and it can also provide the device duty results that are exceeding the 100% of its rating and the marginal, which is in this case 95% of the rating. And the first feature that I'm going to show you is of all the results that's been ran, the program can be able to identify the worst case short circuit current for a given device, and it can be able to display in the one-line diagram. This is very similar to imagining printing all these 10 device duty reports, taking one field at a time and comparing them side by side on a table. That's exactly how this analyzer is transformed for user convenience. So in this case, I have 10 device duty reports, and I have selected the symmetrical fault current, and I have selected the worst case. So the worst case device duty, for example, at bus number 77 is happening with the device duty number 6. And that is what this analyzer is telling you, considering all the 10 device duty reports that was ran. Now, this is where the complexity of the system plays a vital role in identifying potential and special locations that requires extra meticulous analysis and troubleshooting. The first one I would like to cover is the special locations such as the generator circuit breaker. So the generator circuit breaker is handled in such a way based on the ANSI C37 standard that it would incorporate the generator's operating conditions and the system operating conditions to evaluate the momentary symmetrical, asymmetrical, and interrupting symmetrical and the device duty symmetrical peak that is being used for it. So it also gives you the DC component on how much it's been calculated for every single system loading or the generator loading based on the power factor. And again, the program can give you the overall results and the current in different units or in the precision according to the formatting that your client would require. And once this is done, the program can use the export Excel feature to export the results to provide the necessary reports and deliverables. Now, in all these years, we have been considering the device duty results. However, the new enhancement that we have is to also incorporate all the unbalanced short circuit calculations such as several other faults, which is line to ground fault, double line to ground fault, and also the line to line fault. So the greatest feature, the cool feature that I could like to bring up here is with this new ETAP, you have the ability to identify the special locations such as the solidly grounded generators or a delta Y solid secondary side location where the line to ground fault could be greater than the three-phase fault current. And all of these features can be analyzed within a single click of a button. And that's available in this particular option here called Add All Faults Reports Line to Ground. The moment you click on this item, the program will automatically include all fault reports that are based on half cycle, and it would tell the identified locations where the line to ground fault could be greater than the three-phase fault current. So for instance, in this case, the line to ground fault on this secondary side of the transformer, which is solidly grounded, is actually greater than the three-phase fault current, which is clearly evident from the analyzer. Now, in case of dealing with a very complex system where the bus location or the fault location could be all around the place, the new feature that is included in the short circuit analyzer would make the complexity of the system into a much simpler and more easier way to identify is called the OLV autofilter. This is an automatic vision of graphically representing the one-line diagram and filtering out the results associated with that one-line diagram to the analyzer. So in this case, for example, if I would like to select a zone of a particular faulted location, the program, upon clicking the OLV autofilter, will automatically filter out only the highlighted elements in the one-line diagram. And that would give us a great granularity in identifying and troubleshooting smaller piece of the puzzle rather than troubleshooting all at once. And that would help us out to make sure the identification of potential locations or skipped locations or the locations that are having a lot of unknowns can be easily spotted out using the analyzer. The same short circuit analyzer is also extended to view the line to ground reports and their sequence currents and the fault currents accordingly. So in this case, I switch to the all faults menu and I can be able to select the fault type as three-phase, line to ground, or double line to ground, and the corresponding the phase sequence or the sequence currents or the phase currents or the 3I0 current, for example, selecting a line to ground fault, can be displayed among multiple reports, not just one. Imagine printing like multiple pages of reports and you're able to compare only one field at a time between the multiple reports and finding the worst case for an n number of pairs of results is definitely challenging. And in a short circuit analyzer does it in one single click of a button where you can be able to select the phase currents or the sequence currents and select the worst case bolted fault current. You can also include the angle, and that can be added to the include angle option, and it will be giving you the right phasor current for that particular faulted location. Another good item that I would like to show you is now that you have the analyzer results that analyzed the whole calculations and it was able to export it to the deliverables. However, once you picture the final results are being finalized and locked, and you would like to send it to the one-line diagram to display so that the results from the one-line diagram is in sync with the analyzer and the reports and deliverable, can that be accomplished? The answer is yes. All you gotta do is identify the location of the bus and then select that bus and click on the worst case data block option. So the moment you click on update data block, the program will automatically updates the results of the worst case device duty, not only on the faulted bus, but also to all the connected breakers and the protective devices that are directly connected to that faulted bus. And that is one of the important features to make sure that the protective device and the switchgear assembly that you bought from a manufacturer is well properly analyzed and made sure that it passes the short circuit device duty evaluation. So when the service is on, the protective device would protect the circuits and the bus will have a proper bracing rating to make sure that the equipment and the working personnel associated with that equipment is safe. And last but not least, I would like to try on one more application that is very challenging in the recent times is the renewable resources. With the evolution of data centers, several PV arrays and battery energy storage systems and inverter-based applications are being in a rising rage. Now, the most important part is we need to understand that all these inverters are voltage-dependent sources. Basically, they inject current back to the system until the voltage write-through capability is achieved. And all these inverters, based on the short circuit model page, they inject the reactive current to the system based on the terminal voltage of the inverter to a fault that is either remote or local. So here's a perfect example I would like to show where the short circuit analyzer would be of great help identifying the potential terminal voltage for a given faulted location, considering the remote contribution of the inverter. So it will be evident to find out how much current is supplied by the inverter and how long the inverter was sustainable, and then when it was actually turned off by not contributing the current to the system. And last but not least, the device duty and the short circuit calculations such as line to ground, double line to ground, line to line, showing the phase currents and the sequence currents, the voltages, phase and sequence voltages, is also available for IEC standard and ANSI standard. And one last thing is to also make sure the single phase device duty results below a high leg transformer or below a panel systems, whether it's residential or commercial, can also be analyzed using the short circuit analyzer. With that being said, let's move on to the arc flash analyzer that we discussed about and finalize the demonstration on how it is being done for the given system. So let's switch to the arc flash analyzer. As we discussed, the arc flash analysis is very nonlinear. It involves a lot of data collections that needs to be precise, and it needs to make sure that the proper device settings that is actually obtained from the short circuit analysis, thanks to the short circuit analyzer, giving us the right troubleshooting steps, can be well used to determine the relay settings and the protective device settings based on the minimum short circuit current, which is the starting point for performing the arc flash analysis. Now that we identified the arc flash analysis, ETAP arc flash analysis provides the compartmentalized arc flash solutions where the concerned engineer could be able to model a switchgear by selecting different locations for a bus, for an incoming breaker, which is the line side, and another load side breaker, and a load terminal fault, or even to print arc flash labels near instrumentation such as current and potential transformers. So the goal here is the complexity of the system and the non-linearity of the calculations and the equations can easily give us a lot of issues that needs to be carefully looked one by one without compromising the efficiency that is being given to a particular project. And that's where the arc flash analyzer comes into picture. That would basically provide you the following features. You name it, we will show you. The bus arc flash, the source protective device, the load bus, load terminal, load protective device, and the instrumentations are the key locations that can be shown in the analyzer. Now imagine the same thing. Print all the reports for arc flash one by one in a table, and you are able to pick one location at a time and compare it against all the rest of the reports and find the worst case incident energy. Instead of doing that manually, whatever I explained so far can be done in a single click using the incident energy worst case option. From here on, the program can be used very effectively to perform certain critical functions in order to make sure the program is actually established for the given system to identify the potential hazardous locations. So the first thing I would like to say is the details. Every single input data that needs to go into the software for arc flash analysis is now documented in the analyzer. The customer can select the corresponding working distances, the height, width, and depth of the enclosure, the shock protection boundaries, the gap between the conductors, what is the description for this equipment based on the drawings can all be factored into this analyzer and can be displayed to the customer. On top of that, the results such as the total energy, the arc flash boundary, and also the considering the variation of arcing current based on the 1584 equations can also be brought into this program. Now, the greatest challenge is most of the critical fatalities that happen in the industry under the electrical power systems when it comes to human life loss or casualties mostly happen based on arc flash is in the low voltage side. Why? Because incident energy is a function of time. Sometimes larger magnitude of currents would actually operate in a shorter clearing time will give you a high incident energy. On the other hand, small magnitudes of current that are still sustainable could take a longer clearing time of the breaker, which would result in a prolonged extension of the arc flash that could potentially harm or kill a person. In that aspect, what we could do is the software automatically gets the spectrum of the arcing currents that was explained in the generator decrement curve example. The program can list the total arcing current that is operating in the subtransient region, which is in the first cycle range, then in the transient region and in the steady state, and make sure that it is all being seen by the protective device time current curve. And this can be visualized clearly using the arc flash analyzer within a single click of a button. For example, selecting this bus over here and clicking on the time current curve find in star will automatically bring the associated time current curve that is available for this particular bus that is being faulted. And it will also tell what are the total arcing current in the transient, subtransient, and the steady state region. And it would give us a clear understanding graphically and visually saying that, okay, whether this protective device was completely able to see the full magnitude of the current till the last sustainable level and make sure that the energy is accumulated and integrated as an area under the curve. And last but not least, the program also provides you a visual selective coordination view by using the sequence of operation tools. By clicking the right bus and the protective device associated in the zone, this one-line diagram feature available in the analyzer could easily give you the summary of events that could just take place when one breaker operates, which is in the next upstream, the first upstream, followed by the next one, and also followed by the next upstream protective device all the way to the source. And by seeing this animation graphically with an engineer's point of view, the potential issues with selective coordination when it comes to arc flash can be easily visualized and corrected. And same thing, when the system grows really bigger, the program can identify the location of interest using the find button. And there are some important flags exclusively for arc flash, such as if a protective device that needs to clear a fault, but it does not clear just because the protective device is not properly isolated from the impact zone of the switchgear, can also be visualized from the arc flash analyzer. So to summarize, get the correct data into the program that is shown in the analyzer, followed by different locations, identifying multiple system configurations, identifying the generator decrement curve, followed by the time current curves, potentially identifying the maximum and the minimum arc flash, providing a single stop shop to basically show the sequence of operation of events to ensure selective coordination, and selecting the worst case incident energy based on several industry approved standards such as NFPA 70, CSA standards, and the NESC can be done in the arc flash analyzer. Last but not least, once your final results are finalized based on the calculation of the worst case scenario, the program can give you the arc flash labels and deliverables using the e-label maker, or it can also display the worst-case analysis in the one-line diagram and also export it to an Excel sheet that can be given to the client. The ETAP Analyzer is more than just a calculation tool. It's a complete solution for power system safety and reliability. It ensures full compliance with global standards, including IEEE, ANSI, NFPA, NESC, IEC, and CSA, so every study meets the highest requirements. It addresses the rules of device duty, arc flash protection, and protective coordination, giving engineers confidence that equipment is correctly applied and people are protected. From short circuit and arc flash, in both three-phase and single-phase networks, to troubleshoot complex systems, special locations, large data sets, the analyzer simplifies even the toughest challenges. It also provides arc flash mitigation strategies, including maintenance mode evaluations, helping reduce incident energy and keep workers safe. And while it's powerful, it's also simple to use, purpose-built for electrical engineers, support automation, and produce high-quality documentation and labels that are ready for the field. In short, the ETAP Analyzer transforms complex safety studies into clear, accurate, and actionable insights, giving you compliance, confidence, and control. Thank you for your time today. The ETAP Analyzer makes complex safety studies simple, reliable, and compliant. Your next step? Explore how this technology can be applied to your own system and start building safer, smarter power networks today.